In this video, we're going to cover Newton-Cartan theory, which is a version of Newtonian gravity that involves curved spacetime. We all know the simple Newtonian law of gravity from high school physics. During this video series, we've been working up to a relativistic theory of gravity called general relativity, which is much more complicated because it involves tensor calculus. In Newtonian gravity, we calculate the motion of objects using force vectors and Newton's second law, F equals ma. We use Galilean transformations to change between inertial frames, and we have a universal time coordinate t that all reference frames agree on. In general relativity, we have a curved spacetime, and we calculate the motion of objects using geodesics in spacetime. We use Lorentz transformations to change between local inertial frames, and we use an observer's proper time tau to measure time along curves, since the coordinate time changes for each observer. There's a pretty big gap between the simple Newtonian theory of gravity and the complicated general theory of relativity. The good news is that there's a theory that sits in between called Newton-Cartan theory that can help us close the gap. Newton-Cartan theory uses curved spacetime and geodesics to calculate the motion of objects, just like general relativity. But it uses Galilean transformations and a universal time coordinate like in Newtonian gravity. To understand this Newton-Cartan theory, we need to review the Poisson equation for Newtonian gravity. The standard law of Newtonian gravity tells us that the force of gravity between objects is equal to the gravitational constant capital G times the product of the two masses divided by the distance between the masses squared. In this case, the ER basis vector points out of the Earth's center, so the force on the lowercase m mass points in the opposite or negative direction, towards the center of the Earth. We can also rewrite this law as the force equals the lowercase m mass times the gravitational field lowercase g. The gravitational field g is a vector field surrounding a mass that tells us what the gravitational force on an object of mass 1 would be at every given point. The presence of mass causes what we call a negative divergence in the gravitational field. If we have a vector field v, then a positive divergence at a point tells us that, overall, the vectors are leaving a box that surrounds that point. A negative divergence tells us that, overall, vectors are entering this box. And a zero divergence tells us that there are an equal amount of vectors entering and leaving this box. The divergence of the gravitational field at a point is always equal to negative 4 pi g times the mass density rho at that point. This is an equivalent way of describing Newtonian gravity. Now, the gravitational field requires a vector at every point, but it turns out that we can describe a gravitational field using a scalar at every point, called the gravitational potential phi. The gravitational potential is high, far away from the Earth, and low, close to the Earth. The gravitational field is just the negative gradient of the gravitational potential. The gradient normally gives us vectors that point to the highest scalar values, but the negative gradient gives us vectors that point to the lowest scalar values instead. And this is what we want for the gravitational field, where the field vectors point to the lowest gravitational potential. So if we know the gravitational field is the negative gradient of the potential, and sub this into the formula for the divergence of the gravitational field, and then cancel the minus signs, we get Poisson's equation. This tells us that the divergence of the gradient of the potential, also called the Laplacian, is proportional to the mass density rho, where the constant of proportionality is 4 pi g. This Laplacian operator is a bit like a bump detector in the potential. Anytime there's a bump in a scalar field, the gradient of that scalar field will cause vectors to point away from the bump if the bump is like a well, or toward the bump if the bump is like a hill. Since vectors are pointing towards or away from something, this corresponds to a non-zero divergence of the vector field. So the Laplacian operator helps us find bumps in scalar fields, which are basically locations where the gradient of that scalar field has convergence or divergence. So looking at Poisson's equation again, the mass density is always a positive number or zero. It doesn't make sense to have negative mass or negative mass density. So this means that the Laplacian of the potential is always greater than or equal to 0. So this means the divergence of the vector field that comes from the gradient of phi is always a positive number if it's non-zero, meaning the vectors in the gradient of phi point outward. And the scalar field corresponding to this vector field is shaped like a well, since the gradient vectors point to the highest potential. So basically, in Newtonian gravity, mass density creates wells in the gravitational potential, which attracts other mass, since mass always wants to get to the lowest gravitational potential. We're going to use Poisson's equation later, but for now, let's see how we can create a theory of curved spacetime for Newtonian gravity. Now, I'm going to use a common standard in relativity where tensor indices that are Greek letters refer to all four spacetime coordinates, 0 for time and 1, 2, 3 for x, y, z. But tensor indices that are Latin or English letters will only refer to space coordinates, 1, 2, 3 or x, y, z. We're going to start with Newton's second law, F equals ma, and find that it leads to a kind of geodesic equation for the case of a gravitational force. If we have a force that's a gravitational force, then it equals the mass times the gravitational field. We can cancel mass on both sides. Then we can rewrite the acceleration vector as the second derivative of a position vector with respect to time. We can also rewrite the gravitational field as the negative gradient of the gravitational potential phi. We can rewrite this vector equation in component form, where the spatial components of position are x1, x2, x3, and the components of the gradient are the derivatives with respect to x1, x2, and x3. Moving things to one side, we get that the second derivative of xi with respect to time plus the partial derivative of the potential with respect to xi equals 0. This equation kind of looks like a geodesic equation, where we have a second derivative of a coordinate plus something else equaling 0. Let's try to make this equation look more like a geodesic equation. So let's try finding a path parameter lambda and the correct connection coefficients gamma to make these two equations match. First, we choose the path parameter lambda to be the universal Newtonian time coordinate t. Next, let's see what we get when we take the sigma index to be 0. Now, in previous videos on special relativity, I've said that the x0 coordinate is just the speed of light times t. But since we're dealing with Newtonian gravity and Galilean relativity, we're going to say that the x0 coordinate is just the standard time coordinate t, without the factor of the speed of light. So the second derivative of t with respect to t is just 0. Since this term is always equal to 0 regardless of the spacetime coordinates, this implies that the connection coefficients with 0 as an upper index must always be 0. So the upper indices for the connection coefficients are only non-zero for the space components 1, 2, 3. Now the first terms match, but let's look at the second terms. The original equation has no velocity terms, no first-order time derivative terms for the spatial components. This means that the connection coefficients with spatial lower indices 1, 2, 3 must all go to 0. So we're left with only the connection coefficients that have 0, or time, in the lower indices. Now, comparing these terms, we can deduce that gamma I00 must be equal to the partial derivative of the potential by partial xi. This is because the x0 coordinate is just t, and so these two derivatives each become 1. And we're left with our original equation. So we've determined that if we start with the geodesic equation and use the universal Newtonian time coordinate t as the path parameter, and declare that the only non-zero connection coefficients are these, with the spatial index up top and time indices on the bottom, we get equations of motion under Newtonian gravity. So this is like a geodesic equation for Newtonian gravity. So we've found the connection coefficients for a theory of Newtonian gravity. So what's the curvature of spacetime for these connection coefficients? We can use the connection coefficients to calculate the Riemann curvature tensor for spacetime. Since gamma is only non-zero when its lower indices are the time, or 0 index, we can conclude that the Riemann components are only non-zero if this lower index sigma is the time, or the 0 index. And since gamma is only non-zero when the upper index is a spatial index I, we can conclude that the Riemann tensor components are only non-zero if the upper index is also a spatial component I. So the formula for the non-zero Riemann tensor components looks like this. Now, in these rightmost terms, alpha and beta are summation indices, so they appear on the top and the bottom. And since they appear on the bottom, they must be the 0 index if the coefficients are to be non-zero. But this requires that the matching upper indices are also 0. But as we know, this means that the coefficient values go to 0, since the upper index must be a spatial index for non-zero components. So these rightmost coefficients go to 0. And so this is the simplified formula for the non-zero Riemann tensor components. So given this formula and the connection coefficients, we can calculate the remaining 4 cases for the non-zero Riemann tensor components. The 4 cases are where mu and nu are both time indices, where mu is a spatial index and nu is a time index, where mu is time and nu is spatial, and where mu and nu are both spatial. When we set both mu and nu to 0, we just get a term subtracted from itself, so these components go to 0. For mu with a spatial j index and nu with a 0 time index, the second connection coefficient goes to 0 since it has a lower spatial index. And subbing in gamma I00, we get this for the Riemann components. For mu equals 0 and nu equals j, the first term goes to 0 instead, and we get the exact same components but with a negative sign in front. This makes sense because we know that if we swap the third and fourth indices of the Riemann tensor components, we get the same component but with a negative sign in front. And for mu and nu both spatial, both terms go to 0 since gamma with lower indices that are spatial goes to 0. So to summarize all the math we just did, using these connection coefficients, we've found that there are 9 non-zero Riemann tensor components that describe the curvature of Newtonian spacetime, where I and j can be any of 1, 2, 3. But since the order of the partial derivatives doesn't matter, this means there are really only 6 independent components of the Riemann tensor that are non-zero. So in the case of Newtonian spacetime, the vast majority of the Riemann tensor components are 0, and there's only a small number of non-zero components. Now, the standard spherical potential for a planet or star is negative gm over r. If you calculate all the second derivatives of this potential in Cartesian coordinates, we get this expression, which is basically r squared times an identity matrix minus 3 times a matrix of coordinate products with a factor of gm over r to the 5 in front. In 3x3 matrix form, it looks like this. To make this matrix a little easier to understand, we can pick a point above the mass on the x-axis, where x is just the radius r and y and z are both equal to 0. In this special case, the matrix has just negative 2, 1, 1 along the diagonal and a factor of gm over r cubed in front. So this 3x3 symmetric matrix tells us about the curvature of Newtonian spacetime. But how can we interpret this matrix using our intuition? Well, remember from Relativity 107c that if we have a family of geodesics with tangent vectors v and separation curves between them with tangent vectors t, we can use the second derivative of these separation vectors to determine if the curves are coming together or spreading apart. And this separation derivative is given by this Riemann tensor term. If we take the geodesics to point in the time direction with tangent vector E0 and take the separation curves to be in a spatial direction with tangent vector EJ, then we get this, where this Riemann tensor term just gives us the Riemann tensor components we just calculated, which is the second derivatives of the potential. Using the matrix we just calculated for a point on the x-axis above the Earth, this tells us that the x direction has positive geodesic deviation, meaning geodesics are spreading apart in the x direction. But the y and z directions have negative geodesic deviation, meaning the geodesics are coming together in the y and z directions. If we look at what this means visually, if this ball above the Earth follows some geodesics forward in time, it will get pulled apart in the x direction, but get squished together in the y and z directions. This is exactly what we'd expect with tidal forces acting on an object in a gravitational field. So by calculating the Riemann curvature tensor for Newtonian spacetime, we found its components were described by this matrix of second derivatives of the potential, which helped us explain tidal forces in terms of geodesics. We call this 3x3 matrix of potential second derivatives the tidal tensor, since it helps us understand tidal forces. It's also worth noting that if we look at the geodesic deviation for geodesics that are traveling in space directions only, we just get 0 for the terms of the Riemann tensor components. This tells us that, for Newtonian gravity, space itself at a given moment in time is flat. We only see curvature if we look at space-time as a whole. So we figured out that these are the non-zero components of the Riemann curvature tensor. We can now use these to get the non-zero components of the Ricci curvature tensor. Remember, we get the Ricci tensor by summing over the upper and lower middle indices of the Riemann tensor. For this case, the R00 component of the Ricci tensor is the only non-zero component, and it is a sum of 4 Riemann tensor components. Based on these Riemann tensor components up here, the first component is 0, since I and j are spatial components only. And when the 0 index appears in these slots, the component just goes to 0. The other 3 components are just the second derivatives of the gravitational potential along the 1, 2, and 3 spatial directions, which are the second derivatives along the x, y, and z directions. All of this is just the Laplacian of the potential in Cartesian coordinates. The Laplacian of this potential is always positive, since in real life we can only have gravitational potential wells that pull things in, and never gravitational potential hills that push things away. So the R00 component of the Ricci tensor, which is the time-time component, is equal to the Laplacian of the gravitational potential, which, by Poisson's equation, is equal to 4 pi g times the mass density rho. So the Ricci curvature is 0 in the space directions, but it is positive in the time direction if there is a non-zero mass density. This means that geodesics in the time direction will naturally converge together in such a way that volumes will shrink if there is a non-zero mass density in the region. In other words, if we have some mass density surrounded by an imaginary volume, this volume will shrink towards the mass density over time due to the converging geodesics pointing forward in time. So this is a geometrical curved spacetime explanation for why things naturally get pulled together in the presence of mass. Basically, the mass density creates a well in the gravitational potential, which is identified by the Laplacian of the potential, and this potential well causes geodesics pointing in the time direction to converge, as described by the time-time component of the Ricci curvature tensor. So in short, this equation tells us that mass attracts other mass over time. Now, it's worth pointing out that the Ricci tensor equals 0 outside the Earth, because the mass density is essentially 0. But this does not mean spacetime is flat outside the Earth. We know the spacetime outside the Earth is still curved because the Riemann tensor is non-zero outside the Earth. The spacetime curvature outside the Earth causes the shape of objects to change through tidal forces. However, the Ricci tensor cannot detect changes in the shape of objects. The Ricci tensor can only detect changes in volume. Tidal forces don't cause any immediate change in the volume of objects, so the Ricci tensor is not able to see tidal forces. For this reason, the Ricci tensor outside the Earth is 0, even though spacetime outside the Earth is still curved. Now, there is more to say about Newton-Cartan theory, like how we can reparameterize time using an affine transformation, or how the time and space metrics are separated instead of unified like in special relativity, but I'm not going to get into those details in this video. You can check the Wikipedia article on Newton-Cartan theory or Google it for more information. So to summarize this video, we learned how we can rewrite the force equation in Newtonian gravity in the form of a geodesic equation, where the path parameter is the Newtonian time coordinate and the connection coefficients depend on the gravitational potential. This means we can interpret Newtonian spacetime as being curved, described by a non-zero Riemann curvature tensor. The only non-zero component of the Ricci tensor is the 0, 0 or time-time coordinate, and it is equal to the Laplacian of the gravitational potential. By Poisson's equation, this is proportional to the mass density at a point. This means that mass density causes geodesics pointing in the time direction to naturally converge toward each other, which is a new way of interpreting the gravitational force in Newtonian gravity. Now, the mass density rho is not invariant under Lorentz transformations. The value of rho can be different in different reference frames due to length contraction. For example, if we observe length contraction, we might see the same mass inside half the volume, meaning the mass density has doubled. So the mass density is different in different reference frames according to special relativity. This means that rho must be the component of a larger 4x4 tensor, just like how the R00 component is one component of the larger 4x4 Ricci tensor. This new 4x4 tensor that contains the mass density is called the energy-momentum tensor, and it is invariant in all frames according to special and general relativity. I'll talk about the energy-momentum tensor in the next video.